Hello and welcome to Lecture 10 of CHY 113. Believe it or not, yes, we are now in double digits. We are starting to enter into the thick of the semester and really starting to dive into some good chemistry. And so last time we started to discuss stoichiometry. We began a look at how we calculate the amounts involved in chemical reactions and lots of the different tools that are involved in performing those calculations. What today's lecture is going to focus on is how we can use a lot of those different tools, how we can use a lot of the stoichiometric ratios and stoichiometric calculations in order to perform a number of different chemical analyses. In general, I would say that stoichiometry and looking at these amounts in reactions are some of the more common calculations that are done in all of chemistry. For various things, we need to be able to calculate, and for various analyses, we need to be able to calculate the amounts that are involved in reactions. And so we're going to see a lot of that put to use today. The first example that we're going to look at deals with a mineral called thernodite. And you can see a picture of that mineral here. It's just a naturally occurring mineral. And what we're going to look at, what we're going to try to analyze, is the makeup of and the composition of this mineral. And so in this example here, we have a 0.123 gram sample of the whole mineral. And this mineral contains sodium sulfate along with several other different compounds. But the compound of interest for us for this particular problem is sodium sulfate. And what we want to ultimately find, you can see down here, ultimately, we want to find the mass percent of sodium sulfate in the actual mineral. So we have this mineral, the thernodite, and we want to know how much of that, what percent of that by mass is made up of sodium sulfate. And so we have the sample that what we do is we're able to add aqueous barium chloride to our sample. And what that's going to do, we first dissolve our thernodite. We get our thernodite into solution. And then we add some aqueous barium chloride to that. Because what that's going to do is the barium chloride will then react with the sodium sulfate in there and form barium sulfate, which, remember from our solubility rules, is an insoluble precipitate. And so we have this thernodite, just sort of keeping track of where we're at, what we're talking about. We have this thernodite, this mineral that we've now dissolved. And part of the composition of this is sodium sulfate. We want to know how much sodium sulfate there is. And so what we do is we add some aqueous barium chloride, which then reacts with the sodium sulfate to form insoluble barium sulfate. And we know the mass of the barium sulfate that was recovered. We'll use that later in our calculation. So let's take a look at what that looks like. And so what we have here is our sodium sulfate solution. So this just came from our thernodite. And so we have our solution now with our dissolved thernodite in there, which has some sodium sulfate. We have some barium chloride. And so then we take that barium chloride and we add it in to our thernodite mixture, which has the sodium sulfate. And what's going to happen, we can see it here, is that the insoluble barium sulfate is going to precipitate out. And we add enough barium sulfate so that we know that the barium is in excess, and so all of the sulfate is going to precipitate out. The sulfate will be our limiting reactant. We're then able to filter this. So we take this mixture, we mix it around, let it all precipitate out, and then we filter it out and we collect our solid barium sulfate right here. And then we let it dry, and then we're able to find the mass of the barium sulfate. So we perform this reaction. Again, we've got this thernodite, this mineral, that has an unknown amount of sodium sulfate in there. We react that with barium chloride in order to form a barium sulfate precipitate, which we can then filter and find the mass of our barium sulfate. And so the thing that we have to recognize here, remember what we're trying to ultimately find out is in the whole thernodite sample, how much of it was this sodium sulfate. What we have to recognize in this analysis is that all of the sulfate that was initially present is now going to end up as barium sulfate. So all the sulfate in there is going to be converted to barium sulfate because our barium chloride was in excess and our sodium sulfate was the limiting reagent. And so we can look at the equation for that. We started with some sodium sulfate in there. We added some barium chloride. Those are both aqueous. And that precipitated out our barium sulfate. And we ended up with some aqueous sodium chloride as a result of that as well. And so this was our only source of sulfate, was our Na2SO4. And so every bit of the sulfate that was in our initial sample ends up as barium sulfate. And so what we can do is, or what we can recognize then, is that all of the sulfate that we get out as barium sulfate had to have come from the sodium sulfate to begin with. And so if we can find out the moles of barium sulfate that were produced, that's going to equal the moles of sodium sulfate that were present in the start. And so it's a simple conversion then. We're able to, we know how many grams of barium sulfate that we had. We were able to just take the mass of that after we filtered it. We convert that to moles of barium sulfate. We then use our balanced chemical equation, it's a 1-to-1, to convert then to moles of sodium sulfate. From there, we just convert to grams of sodium sulfate, the way that we've been doing for quite a while now. And once we know the grams of sodium sulfate, we know how many grams of the entire mineral that we started with. And so we can just divide that to find our percent composition. And that will let us know the percent of sodium sulfate that was in the original sample. And so we look at those steps. And so we weighed out, again, if we come way back here, we found that our mass of sodium sulfate, the mass of recovered barium sulfate rather, the mass of recovered barium sulfate was 0.177 grams. And so we're able to then, see if I can find it. Thought I could skip right to it. I'm not that fancy. So we recovered 0.177 grams of barium sulfate. We convert that to moles. Use our molar ratio to convert to moles of sodium sulfate. Use our molar mass of sodium sulfate. And so we find that we had to have started with 0.108 grams of sodium sulfate to begin with. We knew that we had 0.177 grams. Sorry, hold on, let me pause for just a second here. Okay, sorry about that, but I knew something just didn't feel right about what I had up there on the slide, so I had to go back through and fix that. And so remember what we've just done then is we've calculated the amount of sodium sulfate that had to have been present in our original sample. We're going to go ahead and take that amount, the 0.108 of sodium sulfate that was present, divide that by the total amount of sample that we had in the beginning, which was 0.123 grams, multiply by 100 to convert to a percent, and we see that the thernodite, the mineral that we had to begin with, had to have consisted of 87.8% sodium sulfate. And so this is called a gravimetric analysis, when we are precipitating out a solid in order to then take the mass of that solid and find out how much is there, and then sort of convert and backtrack back to find out how much of a particular reactant had to have been present to begin with. And so that's one way that we can use stoichiometry to perform some chemical analysis. Another method is determining the formula of a hydrocarbon by combustion. And so remember several weeks ago when we looked at how we can find empirical formula by looking at our percent composition of substances. And some of you might have wondered at that point, and I think I might have even addressed it, sort of wondered, well, what's the point? Why does it help us out to find the empirical formula if that's not the real molecular formula of a compound? This is why it's helpful right here. because what we can do, and we're going to walk through this quite a bit, what we are able to do is charge our iPad or charge our iPencil to begin with, in case I need that. So let me plug that in. Okay. What we're able to do is perform a combustion analysis. If we have some unknown hydrocarbon, some substance made up of just carbon and hydrogen, or even if it's a hydrocarbon with oxygen, but some unknown hydrocarbon. So we don't know what this is. We don't know the actual chemical formula. We just know it has carbon and hydrogen in it. We can send it through a combustion analysis to find out what the empirical formula is. If we then have access to a mass spectrometer, we can find the molar mass of our compound and then take the empirical formula and scale that up to the actual molecular formula. And so that's why empirical formula is an important concept, an important thing to know. Because if we have an unknown hydrocarbon and we can send it through combustion analysis and send it through a mass spec, we can use that to find the actual chemical formula of this completely unknown compound. And so let's take a look at what that looks like and take a look at how we can do that. And so actually, we'll come back to here. And so in the combustion analysis, what we're doing, combustion implies burning, right? And so one of the things that we need to burn anything is oxygen. And so we're going to react our unknown hydrocarbon with atmospheric oxygen, or just add direct O2 to this, and we're going to burn our sample of hydrocarbon. All combustion reactions, especially combustion reactions of hydrocarbons, always produce H2O and CO2. That's all that they produce. If you have a pure hydrocarbon and you combust it, you react it with oxygen, it's going to produce CO2 and H2O. Those will be the only products, always. And so what we can do is we can set up what we call absorbers so that we can collect the amount of H2O and CO2 that are produced. And we don't need to worry about the details. These are just some pretty neat ways that we do it. We can absorb the H2O first using a chemical called magnesium perchlorate. That's just going to absorb all of the water that's produced. The carbon dioxide passes on through. And then we can absorb the carbon dioxide by NaOH using an asbestos support system in there. And so again, don't worry about these details. This is nothing that I'm going to hold you responsible for. But ultimately, just what we need to know from this is that we can burn our hydrocarbon, we can combust our hydrocarbon, and in doing so, we can actually collect the H2O and the CO2, so that we are able to know how much H2O and CO2 was actually produced. We can collect it, we can find the mass of it. So we're going to combust our hydrocarbon, and we know how much of this that we start with. We can combust this known amount of hydrocarbon, and then we know how much H2O and CO2 are going to be produced. So let's look at an example of how we would use this. And so we're starting here with 1.516 grams of some unknown hydrocarbon. Again, we don't know what this is. All we know for sure is that it contains carbon, hydrogen, and oxygen. That's all we know about it. We send it through this combustion reaction, or through this combustion process. And in doing so, we then find the mass of CO2 produced to be 2.082 grams, and our mass of water produced to be 1.705 grams. And so from that, we can actually calculate the empirical formula of this compound. And then in this example, we do have access to a mass spectrometer. So using that, we also know that the molecular weight of this compound is 160.2 grams per mole. So once we find the empirical formula, we can use this molecular weight to find the actual molecular formula as well. And so here's our overall strategy. We're going to calculate the amounts of CO2 and H2O. From that, we can calculate the amounts of carbon and hydrogen that we started with. And from that, we can find our empirical formulas and our amounts of oxygen. Let's take a look at that. So the first thing that we want to do is we want to take a look at how many moles of CO2 were actually produced. Let's take a look real quick at just our generic chemical formula. Hopefully my Apple Pencil has had enough time. Let's just double check, sorry. Let's see if I have just enough charge in this to go on a little bit. 32% ought to cover me. Okay. So let's just take a peek quick at, whoop. Technology is really getting to me today. Let me pause again real quick to take care of my technology. Okay, and we're back. And so let's just take a look real quick at our general formula for this combustion reaction. And so we have an unknown hydrocarbon. So we're just going to use X, Y, sorry. So we know that it has carbon. We don't know how much, or we don't know what the subscript is. We know that it also contains hydrogen, but we don't know that subscript. We know that this one also contains oxygen, but we don't know that subscript either. So that's what we're trying to find, is our X, Y, and Z. So this is a combustion reaction, so we know we're going to react this with O2. And we know that our only products here are going to be CO2 and H2O. Now we can't really balance this yet, because we don't know what our subscripts are. So we're just going to leave this as our general outline for the reaction. Now, note here, as we go through these calculations, that when we look at the carbon in CO2, the only source of that carbon here had to have been from our hydrocarbon. Likewise, the only source of hydrogen had to have been from our hydrocarbon. And so if we can calculate the number of moles of carbon that were produced, that has to be equal to the number of moles of carbon that were present in the beginning. Likewise, our number of moles of hydrogen produced had to be equal to our number of moles of hydrogen that we had in the beginning. And then we'll see how we deal with oxygen. So here we go. So we measured that we actually produced 2.082 grams of CO2. So we first convert that to moles of CO2 using our molar mass. We have 1 mole of carbon per every 1 mole of CO2. So that tells us that in our carbon dioxide that we produced, we had 0.04731 moles of carbon. That's an easy enough calculation. Now we're going to go through our graph to find our moles of hydrogen. So again, just from our given information, we know that we produced 1.705 grams of water. We convert that to moles of water using our molar mass. Then we do have to recognize here that just from our balanced equation, or sorry, from our chemical formula rather, we have 2 moles of hydrogen per every 1 mole of H2O, right? It's H2O. So I have 2 hydrogens for every 1 water. And so I first calculate my number of moles of water, and then I have to recognize that I have 2 moles of hydrogen for every 1 mole of water. So I can see that I also produce 0.1892 moles of hydrogen. And so again, those have to be equal to our moles of carbon and our moles of hydrogen that we started with, because the only sources of those carbon and hydrogen had to have come from our hydrocarbon. And so if we just sort of keep track of that a little bit over here, 0.04731, let's just shrink that down a little bit so we can see it. And so we know that initially we had to have had 0.04731 moles of carbon and 0.1892 moles of hydrogen. So we still need to know how many moles of oxygen that we had present to begin with, though. Now, we run into a problem with oxygen because, first of all, it appears in 2 different places in our products, but we also have it coming in 2 different places from our reactants. And so not all of the oxygen over here necessarily came from our original hydrocarbon. Some of it definitely came just from the oxygen that was being pumped into this system, and we don't have any way of knowing how much that might have been. So we can't do as direct of a calculation when it comes to our amount of oxygen, but we can backtrack this a little. So that's just our reminder of our 2-to-1 ratio there. So again, all it says here is we can't know how much of the oxygen here, how much of it came from our sample or how much of it came from the O2 being pumped in. So we have to go about this calculation in a little bit more roundabout of a way. We know that we started with 1.516 grams of our initial sample. That was just way back in our given information. We had 1.516 grams of our initial hydrocarbon. We also know initially that we just calculated here that we had to have started with this much carbon, and we're just going to go ahead and convert that to moles. Or sorry, we're going to convert that over to grams. 0.04731 times 12 means that we know that we had to have started with 0.567 grams of carbon. We can do the same down here with our hydrogen. We started with 0.1892 grams of moles of hydrogen, which means that we had to have started with 0.193 grams of hydrogen. And so what we're going to do is just take these amounts. We know that we had to started with this much carbon and this much hydrogen. We're going to just take those amounts and here they're just taken out to more significant figures and a little bit differences in rounding, but we're not going to worry too much about that. So our initial amount of sample that we started with minus how much carbon and how much hydrogen we started with, subtract those, what's left had to have been the oxygen that we started with. And so then we can go ahead and convert that to moles as well, and we get 0.0473 moles of oxygen. And so now we know how many moles of each of these that we actually started with. And now it's just an empirical formula problem like many that we've done before. We're going to go ahead and divide each of these by our smallest number. Our smallest number is 0.0473. And so that gives us a 1 for our X value for our carbon, gives us 4 for our Y value for hydrogen, and gives us 1 for our Z value for oxygen. And so our empirical formula is CH4O. And so now we can determine the molecular formula. To find the molecular formula, and this looks complicated, I'm going to go ahead and just skip over that. Let's just come back to here. To find our molecular formula, what we're going to do is take the empirical formula that we've just found, and we've already seen this. We've done this before. We're going to take our empirical formula, and we're going to find the molar mass of just our empirical formula. So we have carbon. We just have one carbon, 12.01. Our hydrogens, 4 times 0.008. Our oxygen, we just have 1 times 15.999. And so the molar mass of just our empirical formula is 32.0. Now we were told way back in the beginning, let's go back here. We were told way back in the beginning of this problem that the molar mass of our whole compound, and so the molar mass of our initial compound was equal to 160.2 grams per mole. So now we're just going to take this 160.2, divide this by 32. So we take 160.2 divided by 32, comes out to 5.0. That tells us our scale factor, how much we need to scale up the empirical formula by to now get to the molecular formula. So we're going to take our Empirical formula here, we had 1 carbon, multiply that by 5. We had 4 hydrogens, we multiply that by 5. 1 oxygen multiplied by 5. We now have a molecular formula. And so this is a formula of, we were able to come up with the molecular formula of a compound that we had no idea what it was. All we did is we were able to take this through a combustion analysis to find the empirical formula, and then use information about our molecular weight to then scale it up to the actual molecular formula. So it's a pretty powerful analytical tool. We're able to find the actual chemical formula of an utterly unknown compound. And so that's a very, very powerful tool to have in our pockets. Now, I know that's a lot. It's a pretty detailed analysis. Keep in mind that on the website, there are some supplemental videos. So if you go to the Unit 2 materials page, video combustion analysis, I do walk through this same exact, sorry about that. I do walk through this same exact example, but it's just in a little more detail. And I actually just looked up to find another example that I will work through myself as well, and post that here too. So you'll have another example, probably just an hour or so after I upload this presentation. And so you'll have another example to go by. Pretty detailed stuff, and I know it's a lot, so I want to provide you with a few different examples to watch. Okay, I'm not going to spend a lot of time talking about concentration today because we've already talked about a lot of this. And so remember that concentration amounts, we're talking about solutions in which we'll have a solute and a solvent. Molarity is something that we've already talked about. And so when we're looking at stoichiometry involving solutions, we use our molarity to go back and forth between moles and liters. And so again, we've already talked about a lot of this, so I won't spend a lot of time here today. It's just still in my slideshow. But we want to remember that anytime we're talking about solutions and we're talking about concentration, we're usually going to be talking in terms of molarity, where molarity is our moles of our solute divided by our volume of total solution in liters. So that's going to become very important for us. And it's just another way that we can convert back and forth to eventually get to moles. So if we know the molarity and we know how many liters we have, we just multiply that to get to our moles. Let's talk about pH just for a little bit, because we've talked about some acid-base reactions. And so when we're talking about acids and bases, we end up talking about concentrations over a very large range. And so we use pH and pOH as a way to more easily keep track of these very large concentration ranges. We use a log scale. And so if you're not real familiar with the math of logs, that's okay. But know that a log scale allows us to work within factors of 10. And so when we calculate pH, pH is equal to the negative log of the hydronium ion concentration. Now remember that the hydronium ion and that H plus is often, or that H3O plus is often used interchangeably with H plus. They're basically the same thing, or they refer to the same thing. So you might see this written either way. And if you recall, that's just the result of when H plus is in water. It's really the hydronium ion which actually exists in there, but we often abbreviate it H plus. And so you might also see, even when I write things, or if you see it in maybe some different source material, you might see pH written as the negative log of H plus. Same thing. If you haven't seen these brackets yet, by the way, these brackets just mean molarity. And so this means, right here, our pH equation just means that pH is the negative log of the molarity of our H plus. So as long as we know that concentration in molarity, we can calculate our pH. And as far as putting this into a calculator, It's pretty simple. I mean, let's say that I want to calculate the pH of a solution in which maybe my H plus equals 1.3 times 10 to the negative fifth molar. So if I want to calculate that, and again, it might be a little different depending on what you're using as a calculator, but you would just, in a calculator like this, you would simply have your 1.33 times 10 to the negative fifth. And I'm going to go ahead and take the log of that, my base 10 log, negative because it's negative log. And so my pH of this particular solution would be 4.88. And so same idea if you're working, see if I can bring it up here, but if you're working with a TI calculator like this, then you're simply going to, what I would do is put this all in at once. I would go negative sign log 1.3 times 10 to the negative fifth. I don't know, let's see if I can get that into the camera. There we go. So I would put it in just like that. If you're using a TI calculator like this, we hit enter, and we get 4.89. Oh, I think I did 1.33 in my example up here. Sorry, same idea though. Okay. And so that's how we calculate pH. pOH is the same thing, only now we're going to take the negative log of our hydroxide ion concentration. That's it, same idea. This is an important relationship to remember. It's not one that we're going to explore much in here or the reasons behind this. Those either go on to 115. You'll talk about the reasons behind this in quite a bit of detail when you're studying equilibrium and acid-base equilibria in particular. But recognize that for any system, the pH plus pOH is going to be equal to 14. And so that's an important relationship for us. Because of we can have questions like this. We want to know the pH of an acid that has a pOH of 11. Or maybe we want to know the pOH of a base that has a pH of 8. Or the pH of an acid with a pOH of 11. And so just several different examples. So remember pH plus pOH equals 14. So the pH of an acid with a pOH of 11 is going to equal 3. If we have a base with a pH of 8, the pOH must be 6. pH plus pOH equals 14. Oh, and it looks like I gave the same exact example again. But you get the idea. And so this is just to show us sort of this log scale. And so if we have a hydrogen ion concentration of 1 times 10 to the negative 1, so 0.1, our pH is 1. Hydrogen ion concentration of 0.02, our pH is 2, and so on. So just to sort of see that relationship. And so try some of these. And so the pH of 1 times 10 to the negative 9th, we plug in negative log. pH of, if we have a hydrogen ion concentration of 1 times 10 to the negative 9th, negative log of 1 times 10 to the negative 9 is going to equal 9. Here we want to know the hydrogen ion concentration if we're given the pH. So we're working back the other way. If we know the pH, and again, this is just a function of how logs work. Don't worry too much about the math of this. But the hydrogen ion concentration is going to equal 10 raised to the power of the negative pH. And so there's a couple different ways that you would put this into a calculator. 10 caret negative pH would be one way to do it. And so you could literally just put this in as 10 and then caret negative 7. So it would look just like this. There we go, just like that on your calculator. Some calculators even have a 10 to the X button. So you can see that I've hit the second, and I'm going to hit, there we go, this button right here on the TI, 10 to the X. And so that would give it to you as well. We do this and we see, we get 1 times 10 to the negative 7th. And so, and remember, and some of this might be review, because you might have seen this probably in some other science classes at this point, but the pH of a solution gives us a way to express the acidity. And this is just sort of just the pH of several different household products, except for blood, probably not a household product. But we can see that blood is pretty close to neutral, slightly basic pH of 7.4, but then the pH of several other different household items. So let's take a look now at what we call solution stoichiometry. For the most part so far, we've looked at solutions sort of qualitatively. And what we've also done so far when we've looked at stoichiometry is we've worked mostly in terms of grams. We've done lots of problems with if you have this much of your two reactants, how much product do we actually produce in grams? Now that we've worked with solutions a fair bit more extensively, this just gives us another tool in our tool belt to now convert back and forth between volume and moles. So instead of a mass of a particular reactant, we could perhaps know the volume of that reactant as long as we know the molarity, and we could convert to moles that way. And so remember, this is sort of the pathway of a lot of the problems that we've done so far. We've looked at the mass of one compound, converted that to the moles of that compound, then use our molar ratio to convert to moles of whatever we're looking for, and then to the mass of whatever we're looking for. So we've seen this flow in problems quite a bit at this point. What we can now do, now that we've been working more with solutions, is, actually back up. So remember, this is sort of the key in this whole thing. And we've looked at that we can go molar mass, but now what we can do is use our molarity if we know the volume. Just another way to get to moles. So if we know the molarity of a solution and we know the volume of that solution, we can use that to get to our moles of whatever compound that we're looking for. Which brings us back to this slide that I showed at the very beginning of this whole unit on stoichiometry. And so a lot of our questions so far sort of focus on this pathway here. That if we know the mass of a compound, we can use our molar mass to get to moles, use our stoichiometric ratio to get to moles, whatever we're looking for, and then the molar mass of that substance, and so on and so forth. So we've sort of been focusing a bit on this path. But we can see now that with solution stoichiometry, and if we know our molarities, there's no reason we can't take this path. And maybe this path over to a volume of solution B. So let's take a look at something like that. And so here, we want to know how many grams of calcium carbonate can be consumed if we have 35 milliliters of a 0.125 molar sulfuric acid solution. Remember when we looked at gas-forming reactions earlier, we saw that one of our gas-forming reactions is the reaction of calcium carbonate with sulfuric acid, that will ultimately produce carbon dioxide gas. And so in this particular question, we have some solid calcium carbonate, and we want to know if we have this much, if we have 35.5 milliliters of 0.125 molar sulfuric acid, how much of this calcium carbonate can actually be consumed by that? And so it's the same type of problem that we've done. It's still a stoichiometry problem, only now in order to get to moles of one of our reactants, we're just going to use our information with volume and molarity. And so we're first going to, I'm not sure why it says convert volume to grams. We're not going to do that. Let me actually go ahead and fix that right now. I'm going to pause you just for a moment. I'll be right back. And I'm back. Probably didn't even know that I was gone. Okay, and so we're going to first convert our volume to moles. I'm catching so many errors in my PowerPoints that I had never seen before. And so we're going to convert our given amount, convert our volume, our 35.5 milliliters. We're going to start by converting that over to moles by using our molarity. And so that's going to be our first step. And you can see that's what we're doing right here. We've got our volume. We're going to convert that over to liters first, and then take our 0.125 moles of sulfuric acid per liter. And so that's now how we're going to get to moles of our sulfuric acid. And then it's a 1-to-1 ratio. We're now going to convert over to moles of whatever it is that we're looking for. And our question wants us to find out how many grams of the calcium carbide are going to be formed, calcium carbonate rather. And so then we're just going to use our molar mass of calcium carbonate for a final result of 0.444 grams of calcium carbonate. And so you can see all that we've done here. Let's come back to sort of our big pathway. All that we've done in this question is we started with a volume of a particular reactant, used our molarity to convert that over to moles, then used our ratio, our stoichiometric ratio, to convert that to moles of what we were looking for. So we had the volume of sulfuric acid to moles of sulfuric acid to moles of calcium carbonate, and then our molar mass of calcium carbonate to mass of calcium carbonate. So we just took this path right here. That's all we did. Still stoichiometry. We're still using our molar ratios in the middle to convert from moles of one substance to moles of another. It's just a difference in how we get to our number of moles when we're going to use our molarity and our volume. Some solutions sometimes, and we'll run into this in lab in a few weeks, but sometimes solutions can't be accurately made by weight or dilution methods if the solute itself is impure or maybe unstable in some way. And so what we can do then in those cases is we make up a solution that's close to the concentration that we're looking for, and we then standardize that solution. We do what's called standardizing that solution against a standard compound. A standard compound is one that is incredibly stable with a very precisely known molar mass that gets us a high number of significant digits. And so we can quite often, in order to standardize a solution, we will perform a titration where we take a measured volume of our solution and add that to a known amount of our standard. And again, we're gonna actually do this and see this in lab in a few weeks. But when we perform a titration like this, an indicator is used to signal the point where our reaction ends. It signals the point where the moles of our standard equal the moles of solute reacted. And so we can then use that to determine the concentration of our unknown solution. And so when we're looking at a titration, when we're looking at sort of this solution stoichiometry with titration, we need to write out our equation, balance the equation, then look at how we convert A over to B, and then we look for our end point. For a lot of acid-base titrations, we use an indicator known as phenolphthalein, which is colorless in acid and pink in base, and we can see that here. So here we have a typical titration setup with a burette. We have a flask containing our unknown solution, or our solution of an unknown concentration down here. We're adding our base to that. And then when the whole in solution becomes basic, we turn pink there at our indicator. Our indicator turns pink. Our solution turns pink with the indicator, rather. And that tells us that the reaction is complete. And so again, I mean, I show this here, but you will see this in lab. We will run some calculations that look like this. My mouse is very touchy today. It's starting to really irritate me. And so here we have just, again, sort of a picture of a titration, what's going on. We're going to add our solution in here. Our reagent, our base that's in our burette, is going to react with the acid that's down in our flask. An indicator will show us when the reaction is complete. And if we remember the net ionic equation between an acid and a base, it's our H3O plus our OH, gives us H2O. And at the equivalence point, when our indicator shows us the reaction is done, we've added exactly enough base to react with all the acid that was in there. So let's just look at an example of what we would do with this. So first of all, we can see here, we're just taking this pathway. We're just going from volume of one compound to moles of another, and then to volume. This is a different pathway in our analysis. So here, we want to know in this question, What volume of 6 molar HCl is required to neutralize 25 milliliters of 0.175 molar NaOH? And then we maybe also want to know what mass is required. Let's just take a look at this problem to start with. And so again, this is all we're doing here is we're taking a different pathway. And this is if we were actually to perform this, we would use a setup just like we were just looking at. But we want to know our volume of 6 molar HCl required to neutralize 25 milliliters of NaOH. So first we want to look at our balanced equation, HCl plus NaOH, and these are both aqueous. We're going to react to give us aqueous NaCl and liquid water. And so we're starting with 25 milliliters of NaOH. We want to convert that over to liters first, because we're working with molarity. Next, we're going to use our molarity to convert over to moles. So we know that our molarity of NaOH is 0.175 moles per liter. That's moles of NaOH. Then we're going to convert to moles of HCl. Again, same exact idea. Now we're going to use our stoichiometric ratio. So that would get us to moles of HCl. We know the molarity of HCl. So if we just sort of carry this through down bottom, because I didn't write small enough. But we know our molarity. Sorry. We want our molarity, our 600 moles of HCl down bottom, so that will cancel out per 1 liter of HCl. And finally, we are looking for, well, what volume? We could leave it in liters, but let's go ahead and convert it to milliliters. And so if we were able to perform this and do this all out, we would come up with 7.3 milliliters. We could also take that to grams. I encourage you to try this on your own, get to 0.160 grams. We also have what we call standardization, in which here we have a sodium hydroxide, an NaOH solution that we don't know the exact concentration of. So we're going to use something called KHP, potassium hydrogen phthalate, which is a primary standard. It's going to react with NaOH in a 1-to-1 ratio. And we would set up a titration similar to what I showed earlier. And we would react this until we get to our endpoint. And here we know that at that endpoint, it took 17.4 milliliters of the NaOH. And we know how much KHP that we start with. And so it's the same sort of calculation. What we're going to do is first, so again, we just know, and we're not going to worry too much about what the actual formula of KHP is, but we know it's 1-to-1. So NaOH plus KHP. KHP is acting as our acid. We're not going to really worry too much about our products over here. We just need to recognize that, like we're told, this is a 1-to-1 ratio. And so ultimately, we're looking for our concentration of NaOH. We want to know our concentration of the NaOH solution here. And so what we have to remember is, like we mentioned with sort of the standardization practice, or with this sort of solution stoichiometry, is that at this endpoint, when I say that I've reached the endpoint of my reaction, my moles, that means that my moles of NaOH that I've added are going to be equal to my moles of KHP that I had to start with. And I knew that it took 17.4 milliliters to get there. And so I need to find first, what are my moles of KHP that I started with? I know that I started with 0.285 grams of KHP. So I'm going to use my molar mass. she said was 204.222. And so I'm going to see that I started with 0.00. I'll carry out my sig figs a little ways and round at the end. So I started with this many moles of KHP. Now again, I know at my end point, my moles of NaOH had to be equal to my moles of KHP. So this means that through this process, I also had to have had 0.0013955 moles of NaOH. How do we calculate molarity, which is what we're looking for? Remember, molarity equals moles divided by liters. I know that I started with 17.4 milliliters. So I'm going to convert that to liters, divide by 1,000. And so then I'll just divide this by my amount in liters, 0.0174. And I will get a final answer of 955 divided by 0.0174 gives me a final molarity of 0.0802 molar. And there it is. And that's a standardization. And so that's it for today. I know that there's a lot, and a lot of this really sort of jumps around. It may take you a few times of watching these lectures and really, really looking through these examples, going back and reading the textbook. It's going to take you a little bit of jumping around, I think, to really get a decent grasp of everything that we talked about today. So I definitely encourage you to do that, to go back and watch some of the videos again. Remember the resources that are available to you on the website. There's all these different videos, and I will add another one for some combustion analysis. Let me just make a reminder to myself to do that. And it will probably even be posted before or right around the same time this video is, but that will be up for another example for you. So just again, make sure that you're making use of all of these different types of different resources that you have. Let's just take a peek at the schedule really quick while I'm thinking of it. Because we do have fall break coming up. That's what I thought. I covered a lot more material today than I had originally planned to. And so there probably will not be another supplemental lecture this week. This pretty much covers all of the information that we were looking for. So over fall break, there will not be, and I'll send an email out too, because I know a lot of you probably still aren't watching the video even. So I'll let you know about this, but I probably will not post any lectures next week. So that will give you time. I was going to take one day off anyway because of fall break. And so that was going to give you a break, but I've covered all the material that I was planning on covering next week as well. And so I'll send out some emails so that we're sort of staying on the right page, or staying on the same page. But this covered everything that I was planning to cover next week as well. So that gives you time to go back and watch some of this, to really go back and get a handle on a lot of what it is that we're doing here. So go back and watch some of these, and as always, send me an email, let me know if you have any questions, and we can try to help you out. And so until next time, have a great fall break too.